Let's meet. My name is Aliaksandr Valialkin. I also known as Valiala nickname in the internet. You can Google by this nickname. And I'm fond of writing fast code in Go. And probably you know me by different Go packages which I created over time, such as FastHTTP, Quick Template, FastJSON, EasyProto, or FastCache, or others. And also I'm a CTO at Victoriometrics. This is a company which creates observability databases for metrics, for logs, for traces. And these databases are very resource efficient and fast. And they are written in Go. So what is a TimeSeries database? Could you raise your hands if you know what is this? Oh, roughly a third of audience knows what is TimeSeries database, but two-thirds do not know, and let's refresh your knowledge. So TSDB is TimeSeries database, obviously, and this is a database specially optimized for TimeSeries data, for storing large volumes of TimeSeries data and for querying this data. And what is a TimeSeries? And the TimeSeries is a series of timestamp plus value pairs, which are ordered by timestamp. And such a pair is known as a raw sample or just sample. So if you hear about ingesting samples into TimeSeries database, then you're talking about these pairs. And every TimeSeries usually has a name. For example, temperature, speed, memory usage, request total, and so on. And also every TimeSeries may have arbitrary set of key value labels. These are just string labels. For example, here is the request total TimeSeries, which has three labels: job, instance, and path. And that's very important that a TimeSeries is uniquely identified by its name plus all the labels per each TimeSeries. So if you see a TimeSeries with the same name, such as temperature, but different labels, such as city Krakow or city Warsaw, these are two different TimeSeries. That's very important to know. And common properties for practical TimeSeries are the following. Sample values are usually just floating point numbers. And the number of samples per each TimeSeries is usually measured in tens of thousands. Why? Because every sample in every TimeSeries is usually calculated with the interval of 10 seconds or 30 seconds. And if you multiply the number of such intervals, calculate the number of such intervals per day for 10 seconds intervals, you'll get this 8,000, more than 8,000 samples per day per each TimeSeries. And usually the number of simultaneously calculated TimeSeries in practice is measured in in hundreds of thousands or millions, in tens of millions, if you use microservices and Kubernetes. Say thanks to these technologies. They increase the number of active TimeSeries significantly. And if you calculate the rate of data ingestion of this TimeSeries into database, multiply tens of millions of TimeSeries by this number of intervals, 8,000 of intervals, you'll get quite big ingestion rate. It is measured in hundreds of thousands of samples per second and more. And if you multiply this ingestion rate by the duration when these samples are stored in time series databases, these are usually months or even years, you'll get trillions. Like in this case, if, for example, if you have time series database with the ingestion rate of 1 million samples per second and multiply by the number of seconds in 4 months, you will get 10,000 of billions or 10 trillions of samples. And please, that's very important. That's not billions, that's trillions. 10,000 of billions. Let's look at the common properties of practical time series for queries. Usual queries select millions of samples over thousands of time series over some given time range. That's a typical practical use case for querying of time series database. And after that, you select these samples and build graph over time for these samples in order to see how this metric for this time series changes over time in Grafana. And usually the query rate for time series is not so high compared to data ingestion rate. If you remember, the data ingestion rate is measured in hundreds of thousands of samples per second, and the query rate is usually much lower, such as up to 100 queries per second. And let's model this time series data for relational database. It will consist of 3 tables. The first table is a series. It contains series ID and series name. The second table, and this table usually contains tens of millions of rows, if you have tens of millions of time series. The second table contains labels for this time series, and it maps key values to time series ID from the first table, and the size of this table is usually 10 times bigger or 100 times bigger than the previous table, because in practice, the number of labels per each time series is around 10 or between 10 and 100. And the last table, the biggest table, is samples table. It contains all the samples, trillions of samples for all the time series. And how do you think how this database will work when you try using traditional databases such as Postgres? Will it work? Okay. Okay. Try storing trillions of rows into relational database and see how it goes. And after that, try querying these millions of samples per query in less than 100 milliseconds. And I bet it will not work. No, it will work if you have millions of dollars and will buy hardware with terabytes of memory and thousands of CPU core. It will work, but not very efficient. That's why these time series databases are needed. And let's look at the requirements for time series database. The first requirement is that this time series database must be able to accept millions of samples per second on a single computer. That's a good requirement, and which rules out traditional databases instantly. The second requirement is that if you multiply the number of seconds to store this collected samples, you will get trillions of samples. And it would be good if you could store these trillions of samples on a single computer. And the third requirement is that usually when you store this time series data into time series databases, you are most interested in recently ingested data and not so interested in old data. And you are interested in the ability to quickly drop old data. And traditional databases do not work well with this unless you use partitioning, manual partitioning over time. But it's a requirement for time series database. And the fourth requirement is to be able to execute these hundreds of up to 100 queries per second, typical queries per second for time series databases on a single computer. And the fifth requirement, if you hit scalability limits on a single computer, it would be great if this solution, time series database, could scale horizontally to many computers. So how to create an efficient time series database? Let's look at some important points which are used in Victoria metrics. And the first point is that very important is to store compactly samples per each time series in blocks, data blocks, which fit CPU caches. Why it is important? Because in this case you can read these small blocks from disk in one go, in one I/O operation, read operation. You do not need to collect many samples from different locations on disk. You just read one block. And when you store samples for a single time series close to each other, then you can compress them very efficiently. Because samples in single time series usually correlate with each other very good. And if you have a good correlation, then such samples can be compressed very well and they could occupy less disk space. And if such blocks of data fits CPU caches, then you can process efficiently, very efficiently, such blocks on CPU, and you can process multiple concurrent blocks on multiple CPU systems very efficiently and scale vertically the performance. The next important feature is to sort samples per each block by timestamp and then store these blocks for each time series sequentially on disk and sort them by minimum timestamp per each block. Why it is important? Because this allows you quickly read multiple blocks for the given time series on the given time range in a very small number of discrete operations because they are located close to each other on disk. And the next important feature is to use column-oriented storage when you store timestamps and values separately. Why this is good? Because in this case, you can apply different compression algorithms for timestamps and for values, which are more optimized for these timestamps and values, and get higher compression rates and lower disk space usage. Then you need to store these blocks in so-called LSM tree, log structured mesh tree. If you don't know what is this, this just a set of sorted files which are sorted by some key. In our case, this key is time series ID plus minimum timestamp per each block, and entries in these files are blocks. And important property of this data structure is that it works very good for data ingestion. It scales very good for data ingestion. And it also provides high performance for during querying of the data, because you can read these blocks sequentially across this data structure. And these sorted files are merged in background into bigger files. You can, when you ingest data, you create small sorted files, and eventually these sorted files are merged into bigger and bigger files in background. And as I said, that this minimizes I/O calls when querying millions of samples across thousands of time series. The next recommendation is to use inverted indexes for fast search over time series by giving label filters. If you don't know what the inverted indexes, these are indexes which map key value pairs for labels into time series IDs, a set of time series IDs, so you can quickly find all the time series for the given key value. And you also can quickly find time series for the given set of key values or the given filters by intersecting these time series IDs for different filters. I also mentioned that it is recommended to partition data by time. Physically partition, I mean, store data for different time ranges into different physical files or physical directories, because it will allow you quickly search for data on the given time range by skipping reading partitions which outside this time range. And it also allows you quickly deletion of all data. You just drop these files or directories, and that's it. And also, it is recommended to use sparse indexes for data blocks stored in LSM trees. Sparse indexes are indexes which contain not all entries for all the blocks in LSM trees, but every hundreds of entries or every thousand of entries. So it contains sparse entries, and it allows quickly searching, locating for data blocks which need to read during queries. But some of these data blocks may miss the data you search because of the sparse indexes. But they are good because they reduce the amounts of data which needs to be read during searches, especially if you store terabytes or petabytes of data. And it improves query performance because of this. And let's look at the Victoriometrics, the time series database, which is open source, and it is optimized for big volumes of time series data. And big volumes is trillions of samples, tens of trillions of samples per each computer. And Victoriometrics uses all the techniques which I mentioned before. And the very important here for this talk is that Victoriometrics is written in Go. And let's look at some performance optimization techniques in Go, which are used in Victoriometrics. So let's start with the most obvious technique. Never, if you want to optimize some program, I do not recommend you starting from just wild guess where the performance must be optimized in which locations of the code. Because from my experience, this doesn't work well, and it will end up in more complicated code, which doesn't work faster. It is very important to start with collecting CPU and memory profiles from production workloads. That's also very important, because if you run some benchmarks, run some tests, and collect this memory or CPU profiles, then this workload can significantly differ from a real workload in production, and you will optimize for artificial workload, and you will not optimize for production. And when you detect this hot pass in your code in production, then you need to think how to optimize them. There is no universal rule how to optimize them, but Go provides very good profilers for CPU, for memory, very good tools, and these profiles are very easy to use, and they do not slow down your program in production, so you can collect the CPU and memory profiles from production systems, and I recommend you doing this if you want to optimize your programs. And then investigate these profiles with GoToolPprof tool and think how to optimize them. You need to pay attention to the top lines in these profiles, because if you will try optimizing lower lines in these profiles, these lower lines usually introduce not so big overhead compared to the top lines, because these profiles are usually sorted by overhead. And as I said before, do not optimize code without benchmarks, because it will complicate your code and will not improve performance, so most likely. And after that, after you identified these performance bottlenecks in your code and try to optimize them, I recommend you to write benchmarks specific for this code pass, a hot code pass. Write these benchmarks, and then run these benchmarks with mem profile and CPU profile options, and collect these heap profiles and CPU profiles. This helps you optimizing this hot pass without rerunning your code in production, your optimized code in production. This reduces your feedback loop significantly and allows you optimizing code for hot pass without running in production. The next important thing which is used in Victoria and I recommend you when you want to optimize programs is to use simple algorithms and data structures. And do not use complicated algorithms and data structures. There is a common wisdom that complicated algorithms and data structures are good for performance. That's not true from my practice. And if you know this big O notation, it also doesn't work great in practice, because this big O notation works great for big n numbers, when this n number leads to infinity. And it doesn't work great for small numbers, and in practice, these n numbers are usually quite small. So do not trust this big O notation during performance optimization. And instead of this, optimize your code for real production numbers instead of theoretical numbers. For example, probably you know that this binary search advanced algorithm, which should work quickly in theory over big lists of some entries, but in practice it works slower than simple scan, linear scan, when you just run a simple loop over tens of items. If the number of items for this search is lower than a few tens, then in 100%, simple linear scan is faster than this binary search. And what I took for myself during this performance optimization is that slices and maps in Go are enough for the majority of performance optimizations. Do not use other data structures. Do not invent other data structures. The next important recommendation is to avoid shared mutable state. What is this? This some memory allocation which can be updated and read simultaneously by multiple coroutines. Because this shared mutable state doesn't scale on systems with many CPU cores. And even worse, with the increasing number of CPU cores, the performance slowdown for accessing this shared mutable state increases significantly. So if you have, for example, a system with 2 CPU cores, then the shared mutable state is okay. But if you have a system with hundreds of CPU cores, then this shared mutable state will be disaster for scalability. And that's very controversial but interesting point is that probably you are aware of this lock-free data structures, and they are recommended the performance data structures. But in reality, these lock-free data structures are based on shared mutable state. They still update and read some memory allocations from multiple routines. And that's why these lock-free data structures are not good for performance optimizations. They also do not scale well. And what is recommended instead is to shard your data, which you need to process among available CPU cores. Usually the number of CPU cores equals to Go max procs in Go runtime, and minimize coordination between Go routines which process this data by processing data in coarse-grained chunks. And if we are talking about time-series databases, then it is recommended to process these chunks and on data block levels. So every CPU core processes some single data block independently of other CPU cores at the given time, and only coordinate when it needs to get the next block for data processing. The next recommendation is to reduce memory allocations. So Go spends less CPU and memory bandwidth on garbage collection. Because you know the Go is garbage collected language, and you need garbage collector needs to visit all the allocated objects in memory. So I have not enough time. Oh, I have two minutes. Okay, it's enough. And the best way to reduce memory allocations is to use memory profile in Go heap profile. And analyze this heap profile with alloc objects option. This option shows you the number of allocated objects per each location in your code since the program start. And this shows the main sources of memory allocations. And if you will try optimizing them, then you will get performance boost. And the best approach to optimize such memory allocations is to reuse these objects via sync pool. And it is recommended that this sync pool is used a lot in Victoriometrics source code. And also, garbage collector needs to scan all the objects in memory, even if, some of these objects which are unreachable, they will be dropped. But the rest of the objects which are still reachable needed to be visited by garbage collector every garbage collector cycle. And this takes CPU time and takes memory. That's why it is recommended to reduce such number of objects in memory which are still reachable. And it is recommended to use collect memory profile and analyze it with in-use objects command line flag, And this command line flag shows all the locations in your code which allocated objects which are still reachable in your code at the moment. And how to optimize it? Prefer structs without pointers if you store millions of such structs in memory. For example, if you create some cache which live across garbage collections. And very important thing is that slices, strings, and channels and maps in Go contain pointers. So if you optimize for the number of live objects, do not use these data structures. And what to use instead of them? Use fixed size arrays instead of strings and slices, because fixed size arrays do not contain pointers, and garbage collector do not need to visit all these objects. And I recommend using some off-heap caches for storing millions of such objects. For example, Victoriametrics uses this fast cache actively. That's off-heap cache. And that's all. Let's conclude this. So the architecture is more important than the programming language for writing performance-oriented applications. And built-in profiler in Go is very good, and I recommend you familiarizing with itself and using it when you need to optimize performance for your applications. And performance bottlenecks usually allocated in very small amounts of code compared to the total size of the code of your application. So you do not need to optimize all your code. You need to optimize only the code in hot paths after CPU and memory profiles show this hot path. And leave the rest of the code readable, because performance optimizations usually worsen the quality of the code. And the Go is very good language for writing very fast applications, and you do not need Rust. That's it. And I recommend you, if you are interested in performance optimizations, I recommend you investigating source code of Victoriametrics and Victorialogs and other projects which are used by Victoriametrics and Victorialogs, because they contain many different performance optimization techniques. That's it. And I don't know whether I have time for questions.
Yes.